coming. It's a very big honor for me to be able to introduce our speaker today, Laure Saint-Raymond. I want to tell you a little bit about her. She got her PhD in 2000 from the University of Paris 7. Then, from there, she went to the Centre National de la Recherche Scientifique. And 2 years later, she became a professor at the University of Paris 6. In 2007, she also joined École Normale, Supérieure of Science. Her awards include a number of things. I will summarize a couple. In 2008, she got a prize from the European Math Society. In 2009, she got the AMS Standard Prize for her fundamental work in hydrodynamic limits of Boltzmann equations in the kinetic theory of gases. I hope we'll get a chance to hear about some of that. And then in 2011, she got the Curie Young Woman Scientist. And then in 2013, she joined the French Academy of Sciences as the youngest member ever of the Academy. And in 2014, she was an invited speaker at ICM. I think Laure is very young, and it's a wonderful honor for me to be able to introduce her here. I would like to say that one of our previous speakers in the Milliman lectures, was also a winner of them. So, very much. Oh, and I should say what she's going to talk about today. So her lecture series has a title From Particle Systems to Kinetic Equations, and as you see, her title today, Chaos and Irreversibility, is slightly different from the one you saw on the flyer, but the content will be basically quantum systems. Thank you.
So thank you very much for the invitation and for the introduction. Fortunately, I will not have to give the English in my lecture because you will see that my English is very poor. But still, I will try to discuss a topic which is, say, at the interface between math and maybe a little bit physics. Because the question I would like to discuss in this series of lectures comes from a very natural question, saying fluid mechanics. As you know, there are many different ways to model and predict the behavior of a gas. So either you consider that the gas is just a system of atoms, okay, and you are interested in describing all the possible interaction between these atoms, and just what you get is a very big system of ODEs, and with a huge number of degrees of freedom. Or you can consider that this gas is a continuous medium, and in this case you have either fluid dynamics, or this kinetic theory that I will discuss, which is kind of intermediate description between microscopic models and fluid models. Okay, so the question that I'm interested in this first lecture is rather the philosophical question about the appearance of irreversibility. As you know, the Hamiltonian system is completely reversible, meaning that if you start from the initial state, you let the system evolve during a time t, and then at time t you reverse all the velocities and let the system evolve during time t, then you get the initial configuration. Okay? And we will see that, for instance, in fluid mechanics, it is well known that you have some phenomena which are irreversible. So this is just a very simple experiment that I have realized in my kitchen. So I'm not an applied mathematician, but that's, you can do the same with a very without any material except for this. So this is a very simple experience, except that, as you will see, it's very difficult to realize. Okay, so what I told my kids is that if they were able to do the same, they authorized to eat all the sweets, but of course they tried during a long time and they never managed to do the same. Okay, so what I would like to do is to explain why this kinetic theory, which has been introduced by Boltzmann at the end of the 19th century, is a very a simple equation, simple PDE, which shows to explain this kind of behavior, okay? Or which says why we cannot see this kind of behavior. Okay, so maybe first of all I have to introduce a little bit this theory, and then I will discuss the connection between this theory and microscopic dynamics. Okay? So the idea of Boltzmann is to say that if you have a very large system of particles, then it's very complicated to get a precise determinist description of this system, and then you can just try to get a statistical description of the same system, meaning that the unknown in this theory is a probability, and I think this was the first time that the evolution equation was written for a probability. So this probability is just the ratio between the number of particles having position x and velocity v at time t and the total number of particles. Of course, this can be a continuous function of x and v if we decide that you have continuous position. Okay, so say from the physical point of view, this function is not something that you can measure with some tools. Okay, but this is a more precise, it gives more precise information, as you can recover all the physical quantities just by taking average of this function f. Okay, so for instance, density, the local microscopic density of the gas is just the integral of f respect to v. The bulk velocity would be, say, the integral of v respect to f, and the temperature will be just variance of this probability density and so on. Okay, so all these quantities that you are used to use for, say, macroscopic description, you can recover them from the f just by taking some average function. Okay, so now what you are interested in is to write an evolution equation for this f, so as to predict the behavior of your gas. Okay, and so here I will focus on a very, very simple system which just consists of half spheres. So essentially you have two different phenomena. The first one is just transport, meaning that if you are in a vacuum, you just look at one particle and say that if you have a straight motion according to straight line with constant velocity, and then the position is just given by this very simple differential equation, dx over dt is equal to v, but v is just a constant. Okay? Now here we will have another phenomenon which is collision. So you imagine that your particles are very small balls of radius epsilon, and then at some point they may collide. I think that's just interaction like this. And here we'll assume that you get the velocity here, v1 and v2 after the collision in terms of v'1 and v'2, which are velocity, say before the collision. And in terms of here the normal vector x1 minus x2. Okay? So the main assumption in this model is that the collision are elastic, meaning that the momentum is preserved, so the sum of v1 plus v2 is equal to the sum of v'1 plus v'2, and the kinetic energy is conserved as well, so v1 squared plus v2 squared is equal to v'1 squared plus v'2 squared. And then you have just one possibility to get the non-penetration condition here. So this is just specular reflection with this normal here. Okay? So what I say that once I have prescribed the boundary condition and all dynamics is completely known, and then I can write an equation for f which corresponds to this phenomenon. Okay? So this equation is a little bit complicated, but I will try to explain it a little bit. So just for the moment, forget about the right-hand side and just look at the first, the left-hand side. So this is what we call free transport, and you can check that if you look at f of x plus dp, okay, F. And so it will be 0 for free transport, meaning that F is transported along the characteristics of free transport. Okay, so this exactly corresponds to just transporting vector. Okay, so this first part, this left-hand side, just corresponds to this free transport. Okay, and then you have this very complicated thing on the right-hand side, which corresponds to the effect of collision. So I will try to explain a little bit. So here you have a term with plus sign, so F is a probability, so something which is negative. Okay, so the gain term corresponds to the fact that you can treat a new particle of velocity v just by collision with two particles of velocity v prime and v prime prime. Okay, so here you start from two particles of velocity v prime 1 and v prime 2 at the same position x at the same time t, and they collide, and with some probability they will generate two new particles with velocity v and something else. So anyway, what you get is that the probability of finding this particle of velocity v will be increased by this collision. Okay? And then you have this last term here, which has another sign, and it corresponds to the fact that you can have a collision between a particle of velocity v and a particle of velocity v2, and they will just create some particle with other velocities. So this tells you that the probability of having a particle of velocity v will just decrease. Okay? So this is, say, what this right-hand side is expected to express, and then you have this term here, which is called the collision cross-section, which tells you the statistics of this jump process. Okay, so you see that here it's a little bit different from what I've drawn in the previous picture, because here the size of the particles is just 0. Okay, so the two particles are exactly at the same position, and then you have here something which is like a random process, random jump process, and the particle just change their velocity. Of course, the particles, they do not disappear, they just jump in the phase space. Okay, so and this collision cross-section here, so this is the one that you obtain in the case of art spheres, but this is somehow characteristic of the kind of microscopic interaction that we consider. If instead of this purely specular reflection for art sphere, you say take another interaction potential, then you will change just this collision cross-section here, but the general form of the operator will be the same. Okay? So I will not give you a very precise theory for this equation, and actually it's very complicated. So I would like to tell you a little bit more about, say, the important physical features of this dynamics. Okay? So just maybe just to let you know. So the fact that this solution has, say, global solutions for all times is, say, independently of the size and the regularity of the initial data, is something which has been proved by Milliman and Laure, so maybe something like 30 years ago, 20 years ago. Okay, so but this is not the point here. So let me explain one of the important properties of this equation. So here, very quickly, this first identity, but maybe I can just try to explain it a little bit more. So Q of FF is just the right-hand side of the previous equation. Okay. So and now I would like to integrate this right-hand side with any function of v. Okay, just forget about the t and x for the moment, and I'm just addressing this one. So what I say is that as particles cannot be distinguished, you get some exchangeability between particle number. You see that particle number 0 here and particle number 2. They are exactly symmetric. Okay, and you see that you can also change v prime 2. So you have this symmetry between v and v2. Of course, if you integrate only with respect to v2, this is no more symmetric. But now if I multiply by a function of v and also integrate with respect to v, you see that everything is symmetric between v and v2, so I can just change here this expression, and what I get is, so this is the short notation for f of b prime, f of b prime 2 minus f of b, f of b2, and then I can just say that this is 5 plus phi 2, of course there is something 1/2, and then you have this cross section, dv, dv2. Okay, so this first property is just due to the fact that all the particles are exchangeable. Okay? And there is another important property, which is the fact that at the microscopic level, the collisions are completely reversible. So if you start from two particles with velocity v and v2, you can get the particles with velocity v prime and v prime 2, but then if you just exchange particles, you can just go back. Okay? So now what I say is that here I can exchange the pair VV2 and the pair V prime V prime 2. Okay, this is just an evolution. Okay, so if you do that, what you get is 1/4, and then you get F prime 2 minus F 2, and then you get, of course, here you have the sign minus, so what you get is 5 plus phi 2 minus phi prime minus phi 2, and then you extend VV2. Okay, so the first one here is just due to exchangeability, and here the second one is due to the fact that the collision at the microscopic level are reversible. Okay? So now if you use these two important properties, you get this identity, which will be crucial for the sequel. So the first remark is that if you take phi to be 1, function 1, constant 1, of course 1 plus 1 minus 1 minus 1 is always 0. Okay? So this tells you that if you integrate q of ff against 1, you get 0. Okay? So you can go back to the equation, multiply the equation by 1, integrate with respect to v, and what you get is this first conservation here, which is the conservation of mass. Okay? The integral of f dv is just the local mass, and this here is the divergence of the integral of f dv, which is just the momentum, the average momentum. Okay? So what I say is that the integral of q of ff against 1 is just 0, and this is just the fact that the total number of particles is constant. Okay? So this is a local property, but of course, in average, it's still true. Okay? Now you have the same for if you take phi to this function v, because by assumption you have that v plus v2 minus v prime minus v prime 2 is equal to 0. Okay? This was the conservation of kinetic momentum, which comes from the fact that the collisions are assumed to be elastic. Okay? So you see that this is exactly the same. The integral of q of f against v is just equal to 0, and you can just multiply the equation by v and integrate, and the right hand side is just 0, and you get that here the conservation of momentum, so this is the momentum, and here you have something which is just the momentum flux. Okay? And then you have the same for the energy, because each micro-collision preserves the energy. You know that in average, the energy will be preserved. And so taking phi to be v squared, you see that the right hand side here is 0. And so here you get that the kinetic energy will be constant. Okay? So this is really important because this tells you something about the relation between the Boltzmann equation and fluid mechanics. Okay, if you look at this equation, actually they are very similar to the Euler equation for perfect fluid. Okay, this is just conservation of mass and energy. The only difference is that, in general, there is no reason why F, so this momentum flux and energy flux could be expressed in terms of density, temperature, and velocity. Okay? So in general, this system of equations here is not closed. Okay? What you need is some state relation. Okay, so what I say that kinetic theory is a little bit more precise than usual fluid mechanics because it doesn't assume that the fluid is at thermodynamic equilibrium. Okay? But this is a connection between, say, kinetic theory and fluid mechanics. So this is the first important property of the Boltzmann equation that is consistent with fluid mechanics and is consistent with the assumption that you have this collision which are elastic. quantity which actually come from the same identity. So if you take now 5 log of f, you know that the log is additive, so log of f plus log of f2 is just the log of ff2, and the same for log of f prime f'2. Okay, and now you also know that this is an increasing function, and so this function here, the integral of q of f log of f, has a sign. Okay, so this is exactly what is written here. You know that the integral of q of f log of f is always non-constant. Okay, so this just comes from the structure of the equation and this very simple symmetry of the collision current. Okay, so but now this has very important consequences, because you see that if you multiply the equation, so the Boltzmann equation, which says dtf plus v equal x f equal to q of f. Okay, the equation that I'm talking about is just this equation, q of f. Okay, so now you multiply this equation by log of f. So in the right hand side, you integrate with respect to v. So in the left hand side, you just get the integral of f log f. And here you get this quantity which is the sign. Okay, so what this tells you is that this quantity, which is, so I will try not to be confused with this, but this is the entropy for physicists and the opposite of the entropy for mathematicians. Not really, but it's like this. Okay, so this quantity, which is the entropy, is an increasing function of time. Okay, and this is very important because I come back now on my very preliminary remark about reversibility. You see that now this dynamics here is not reversible. If you start from an initial data, okay, and you let the system evolve during time t, you see that this quantity here will be increased. Okay, now you just take all the velocities and change the velocity in their opposite. Of course, the entropy will not be changed. Okay, and you let the system evolve during a time t, and you see that this quantity here will be still increased. Okay, and so you see that you cannot be back to the same configuration as at time 0. Okay, so you cannot just go back to the initial configuration, except if this initial configuration is in equilibrium. Okay, so see that I've told you that this equation should describe the same dynamics as my Hamiltonian system, just my R sphere dynamics. But you see that this is not the case, because the first one is reversible and this one is not. Okay, so this is really something which is important to understand in this transition, and something that I would like to insist on, is why this model is not reversible, why the Hamiltonian dynamics is reversible. Okay? So now what, say, last thing I would like to comment about this Boltzmann equation is, say, what happens for very long times. Okay, so we have this entropy, which is an increasing function, and so the question is, will it converge to infinity, or will it converge to some maximum, or so what happens for very long times? And the point is that you can check that the entropy, provided that you have fixed both the mass, the momentum, and the energy. Okay, so you have fixed the integral of f, the integral of fv, and the integral of fv squared, and the entropy as maximum. Okay, so this is a very simple, of course, everything is formal for the moment, but this is a very simple application of Lagrange theorem. So if you take the function of the entropy function, it's just the integral of f log f. When you differentiate this function, you get log f, and you know that, say, you will get a maximum or minimum when this is just a linear combination of the differential of the mass, the momentum, and the energy. So for the mass, it's just 1, for the momentum, it's just this in this case. Okay, so we have here some alpha, some here. Of course, in order that you get an individual function, this gamma should have sign. There is a different condition. Okay, so just to summarize, what you get is a dynamics for which you'll have this entropy which is increasing and which converge for a very long time to this distribution, which is nothing else than a Gaussian. Okay? You get that f is just something like constant times the exponential of minus u squared. Okay? And this is exactly consistent with the equilibrium predicted by microscope. Okay? So you see that already at this microscopic level, which is not fluid mechanics, but something kind of intermediate, we have this appearance of irreversibility and the appearance of some factors of dynamics. Okay, so this is a very general picture of say, different level of description for, say, a very simple perfect gas. Just take this out-sphere dynamics. So either you would like to have a very microscopic description and you just get a system of n particles of size epsilon, and then you just write Newton's equation for all these particles. Of course, you get something which is, so we cannot say anything but the quantum measure. Say at the very end, what you would like to obtain is this fluid mechanics. Okay, so either Euler or Gibbs's equation, something like this. Okay, and say in between you have this description by the Boltzmann equation. So let me just tell you that, say, in principle, this is the same level of description as the microscopic dynamics, as you are interested in the position and velocities of all the particles, but instead of having all the particles, you are just increasing some statistical description. Okay, so in principle, this is the same level of description, so still keeping track of all these particles. It's a particular description, but there is a big difference between these two, which is the fact that one is deterministic and the other one is a statistical description. So it will say something about an average motion or something which is highly probable, but not something deterministic. And this is exactly why you have this apparent paradoxes on the reversibility axis. Okay? So we're not comment on all this transition between kinetic theory and hydrodynamics. This is something I worked on earlier, but I cannot say everything in 1 hour. So there are mathematical difficulties for this, but at least at the formal level, it's something which is very well understood. Okay, so right now I would like to explain how to get to the formal level the Boltzmann equation from Hamiltonian system. Actually, Hamilton, of course, it's a little bit singular, but you can do the same for any Hamiltonian system with a compactive force interaction. Okay, so here I will not give mathematical reason to this part. I just would like to underline what are the crucial assumptions and scalings, and so what are the underlying assumptions when you use this kinetic theory. Okay? So the first obvious remark is that this is a statistical description, so of course you need that you have a lot of particles. Okay, if you have just one, it's not very easy. Okay, and this also means, as I told you, that the Boltzmann equation will tell you something on the average and not on some particular deterministic trajectory, in some particular dynamics. Okay, so this means that, of course, you can have other behaviors. Okay, so for instance, this very small field that I have shown at the beginning, this dynamics may exist. Of course, this is if you just go back to get this one. But what I will try to explain is that it is not taken into account in this Boltzmann description just because it's highly improbable. Okay? So if you are interested in statistical description, instead of say, a system of ODEs for the Hamiltonian system, for the system of particles, you would be interested in how you will just transport any initial configuration of your n particles. Okay, so you are not interested in one particular trajectory, but say, put some measure on the initial data and look at how it will be transformed by dynamics. Okay? So this means that the kind of object you are interested in is a function like this, which depends on a lot of variables, which are all the positions. So capital Xn is just for the n position of the n particles, and capital Vn for the n velocity of the n particles. Okay, so the very first object that you would like to consider is this density on a very big phase space. Okay, so the joint probability of finding all these n particles with this position here and this velocity. Okay, and so in this for this probability density, the equation is very simple. Because actually the dynamics is very simple. See that for R spheres, you have only transport, okay? And the only thing that can happen is that at some point particles will collide, meaning that you will be on the boundary of this domain here. So the domain is the set of all position and velocities such that any two particles will not overlap. Okay? So the domain is this domain here. Inside the domain, you have only free transport, meaning that you have this equation dtfn for the sum from I equal 1 to n of vi equal xi fn to 0. And the collision are just the boundary conditions. Okay? So once you are on the boundary, you have this specular reflection on the boundary. Okay? So this is just a boundary condition. Okay, and this is completely equivalent, okay, to the dynamics of a system of particles, meaning that if you start with Fn, which is just a direct mass, well, you get its direct mass or its trajectory. Okay, so at this point, everything is exact. Okay, but of course, you are not interested in this function because one trajectory is something which is difficult to describe, and of course, the probability, the set of probabilities of the set of trajectories, something which is very complex. Okay, so the only thing you are interested in is, say, the probability of finding one particle, one typical particle. So if you assume that Fn is symmetric, meaning which corresponds to the fact that all the particles are interchangeable, and what you are interested in is just the first marginal of this function. Okay, so you take this function, which depends on n position, n velocities. You vary with respect to all position, all velocities except one. Okay, and you get a function which, say, lives in the same phase space as the solution of the Boltzmann equation. Okay, so this function now depends only on one position and one velocity. Okay, so what you expect is that you can say something about this marginal, and that this marginal should be relative to the solution of the Boltzmann equation. Okay, so you see that this is exactly at this point that you are missing a lot of information because you are very with respect to everything except for one position and one velocity. Okay, so this is the first important thing that you have to remember, that you have only something which is a statistical description and which only tells you something about average. Now the second important ingredient is the scale. Okay, so here what you would like to say is that essentially during a time 1, what you will have is something like, so here I have this factor alpha, so I would like to have, say, a finite number of collisions and a finite distance on which the particle is transported. I would like to have balance between the two phenomena. Okay, and when I say that this is actually a computation which goes back to Maxwell, okay, so you have n spheres of size epsilon, and for the moment I assume that all these spheres are just fixed on lattice, and I would like to know if I have another particle, what is the probability for this new particle, the red one, to have a collision with one of the scatterers. Okay? So you see that, so either you can say that the particles are fixed, you just look at this red particle, or you can say that you are in the framework, the reference frame of the red particle, and then you see all the other particles which are moving. Okay? So this means that the volume occupied by one particle like this, if the real size of the particle is epsilon, the real diameter, see that you have epsilon to the d minus 1, which is the section here, and during gravity, what you get is that, say, the length of this cylinder is just like the velocity times the diameter. Okay, so this is exactly this one. Okay, so the volume occupied by the particle during time t is something like this. Now we have n particles, so the total volume occupied by the particle is n epsilon to d minus 1. And you see that if you would like to see, say, alpha collision during each unit of time, you need to assume that n times epsilon to d minus 1 is equal to alpha. Okay, so this is, say, roughly the argument of Maxwell to get the scaling, right scaling, to get this kind of description. So there is an important remark that if you now look at the total volume occupied by the particle, the static volume, of course it's just n times epsilon to d. Okay, so if n epsilon to d minus 1 is finite, n times epsilon to d is something which converges to 0. Okay, so this means that this Boltzmann equation is not a description which is valid for any gas or any fluid, but just for perfect gas, where you have no excluded volume. Okay? Okay, so this is the second important thing. So when you expect that you will have description by the Boltzmann equation only in the limit when n tends to infinity, epsilon tends to 0, and you get this scaling relation. Okay, so it's a statistical, so you will have something which is only a convergence to probability, and this is a convergence, so something asymptotic with an error of term. Okay, so this is really important to understand. So now in this low density limit, so low density or Boltzmann right is the same, just a scaling assumption that n times epsilon to d minus 1 is equal to something on the order of 1. Then you would like to write the equation for the first particle. Okay, so you start from this transport equation for Fn, and you just integrate with respect to all variables except for x1 and v1. Okay? So of course you get the transport, dt plus v1 plus x1, and then the first particle. And then what you get is not 0 because you have a boundary term. Of course, your domain is a boundary where you have this non-overlapping condition. So you know that the particle number 1 has to stay at a distance which is at epsilon of any other particle. Okay, of course, any other particle, there are n-1 such particle, and they are all exchangeable, so you can just look at the direction with this particle number 2, which is written here. And so you see that n-1 is just for the number of possible, say, number of different components of the boundary. Then epsilon to the d minus 1 is just the surface of the sphere, okay, so the size of the boundary. And then you have this formula here, which is just Green's formula for integration. Okay, so you get something like this. This is nothing else than Green's formula. Okay, so you see that this is, if you now take n times epsilon to the d minus 1 is equal to alpha, you see that this looks like a little bit like the Boltzmann equation, provided that you split the integral into two different terms according to sign of this quantity here. Okay, so either the sign is minus, and then you just set everything like this, or the sign is plus, and then you use the boundary condition to write everything in terms of the three-dimensional velocity. Okay, so essentially you get an equation which is very close to the Boltzmann equation, except for one thing, which is really important, and which is, say, the main thing we will have to discuss in the Supra, which is the fact that if you really look at the equation, so up to some error, what you get is something like this. This means that actually, of course, the probability of having a collision in general has no reason to be something which is a product. Okay? In general, the probability of having two particles at the same position with different velocities is just the joint probability, so this is the second marginal of Fn. And in general, that this has nothing to do with the product of F1. Okay, so the crucial assumption in kinetic theory and all this mesoscopic description of the gas is this what is called this Gauss assumption that the second marginal, so the joint probability of finding two particles with say position prescribed position and velocity is equal to the product of the first marginal. Okay? So this is something which is really important. So this means that you expect all particles which will collide to be independent. Okay? That there is no correlation between particles when they will collide. Of course, after the collision, we will see that if they just collide, we expect the particles to be correlated, but before they collide, they should be independent. Okay? So, of course, this identity for fixed n and fixed epsilon it cannot be true. Okay? This equality cannot be true. First of all, because even at time 0, it cannot be true because of the exclusion. You know that particles have to be at a distance at least epsilon, so this cannot be true. Okay. So, but you can say that asymptotically, when epsilon tends to 0, of course, this is almost true. But then what is wrong is that such, say, something like this cannot be preserved by the lattice. Okay? So this is what we have to prove is that it will be still almost true in the limit. Okay, so this is really the main thing that you have to check if you would like to give a rigorous description, a rigorous derivation of the Boltzmann equation from the Hamiltonian system, is that you are able to prove again this Gauss assumption. Okay, so this is really the heart of the proof. Okay, and this is I think the main breakthrough in Nashville's work. So actually, as far as I know, this is the best reason we have to describe this low density limits up to now. So this is a result, I think, something like 1975. Even though the proof was not pretty rigorous, let's say, this strategy. Okay. So the theorem can be roughly something like this. So you start from your system of n odd spheres on, say, on torus, because boundary condition is not a problem. And you assume that initially they are independent. Of course, this cannot be completely true because of the exclusion, but say up to the exclusion. And identically distributed with a function f naught. And the only thing that you assume on f naught is that you have a sufficient decay at infinity. Okay. Then you can prove that in the Boltzmann grand limit, so this is something which is asymptotic, which is only true in the limit when n tends to infinity with this Boltzmann grand scaling. But you can prove that the first marginal of your true solution of the Liouville equation, so which is the description of the typical particle, covers almost everywhere the solution of the Boltzmann equation, so like the one that we have discussed in the beginning. But of course, say the main restriction is that the result is only true for a very short time. And when I say very short, is say less than the average time for the first collision. So from the physical point of view, it's just ridiculous because you prove that in the limit you have something which is a collisional model, but provided that you have no collision extension. Okay? That's okay. So this is the mean time for the first collision. So this means that essentially you will have still something like capital N over 2 collisions in your system. In particular, this tells you that what you expect is to get hydrodynamics in the limit when this alpha, which is the Newton number, tends to 0, tends to infinity, and you see that essentially you get something just for time 0. Okay, so this is of course the main restriction in this theorem. First of all, because you will not see any relaxation. Okay, the relaxation is something that you see for long times or for large alpha, and of course here the result is only true for just a fraction of mean free time. Okay, so particular, you cannot say anything, say, on the transition between particles and fluids. That's really important. Okay? And what I would like to say is that actually this result is not very surprising. Because if you go back to this Boltzmann equation, so now we assume that you can Gauss assumption and can write this. You see that this operator here, of course, it's like a convolution in V, but in T and X, this is just a multiplication. Okay, T and X, they are just parameters in the equation that grow. So the equation that you have is something like dtf with very grad xf equal to alpha and something which is like f squared. Okay, so the very first result that you can get from the equation, say, for construct solution with the equation, just forget about the transport, so just something like dtf equal to f squared, alpha f squared, and you know, if you just forget about the minus sign, from the compensation between the gain term and the loss term, you get something which is like the reverse equation, or easier, something like dtf equal alpha f squared, and you know that you have some lower function, like whatever alpha. Okay, so this is not very surprising. So the method is really something which looks like this will be based, I will try to explain, on some application of Curie-Curie's theorem, but essentially what you do is exactly the same as looking at the equation dtf equal alpha f squared. Okay, so this is not very surprising that you cannot go for a very long time. Okay, and if you would like to construct a solution in a large for the Boltzmann equation, then you need to use the dissipation. The fact that you have the dissipation of entropy, and so this is much more involved, and you have no counterpart at the microscopic level. So this is why, for the moment, it's essentially the optimal result. Okay, so this is the first comment about this result. The second comment is about this chaos property. So one thing which is really important is that you prove, say, from the strategy of Lanford, you will never prove directly the fact that you have chaos, meaning that you have independence between the particles, or meaning that the second marginal can be expressed as the product of the particles. Never. Okay? The proof is a little bit strange. What you will prove is that you will, so for any finite order marginal, so instead of looking just at the first one, you look at all finite order marginals, you will get a kind of very complicated system of equation for these marginals. So hierarchy, which is called the UVGKY hierarchy. Okay, so you can take limits in this system, you get an infinite system, and just in the very end, you just say, oh, but this system has a very particular solution, and this solution is factorized. Okay, so this means that you get the chaos just as a consequence of the fact that the limiting system has a unique solution, and that the solution is factorized. But there is no argument which tells you that you have chaos for another reason. Okay, so this is really strange that you will never prove directly the independence, but just get this as a consequence of the more general reasons. So in particular, this tells you that this is very inherent to the particular form of the initial data that you consider. If you consider other kind of initial data, so initial data which are not chaotic, which are not, or even have not this asymptotic independence between the particles, then you cannot obtain other dynamics. Okay? So this is something to do with. And say now the last but not least, this question about reversibility. So as I told you earlier, there are two apparent paradoxes. The first one is the fact that the Boltzmann equation is not reversible because you have this École functional. And the second one is the fact that the Boltzmann equation has an attractor, which is of course not the case for the system of particles. For a system of particles, you have the Poincaré recurrence, which tells you that you will of course no attractor. Okay, so this is maybe the only thing that I would like to explain a little bit more today, which is very formal arguments. And then tomorrow I will try to explain not in detail, let's say, the structure of the proof for this theorem. And then in the third lecture I will try to explain some improvements, so how we are able to get very long time asymptotics in the case where you start very close from the equation. So this means that, for instance, we are able to derive some linear fluid models such as Stokes equation or Stokes equations. Okay, so let me just comment a little bit about these paradoxes. So as I told you, one thing which is pretty important and which is kind of, say, a very early idea of quantum mechanics is that the Boltzmann equation is not a deterministic prediction of dynamics. Okay, so this just tells you something about the average. Okay? So in particular, this means that there are plenty of bizarre dynamics, especially the one that I have shown on the field. And these dynamics, they exist, but the only thing that this theorem tells you is that they will arise with very small probability. Okay? And so you see that actually the result is a little bit more than just the average. What it tells you is that this probability which converges to 1 in limits, you get the Boltzmann dynamics. Okay? And so there is a question which is, where does the relativity come from? So the explanation is something like this. So you start from the initial time here, and each time you have a collision, you lose a little bit of the information. Okay, so what you have to understand is that the entropy, this Lyapunov function, or the opposite of entropy, is something which tells you how, what you know about the correlations. At time zero, you know that there is no correlation, so you have all the information about the system. And then each time you have a collision, of course, you have a little bit of correlation, but you forget about this correlation. Okay, in the description that you have, you just do as if everything remains uncorrelated. So each time you have a collision, then you lose a little bit of information. So you see that this irreversibility is not to understand in the sense that you have a sense of time, that should be a philosophical notion, but just the fact that you have an initial time, a time which is very particular, for which you have all the information, and then you can go backwards or forward. This is exactly the same. Each time you are a little bit further from this time, you have lose a little bit of information, and so you cannot go back. Just because you have lose information, so you cannot go back. And so it's really important that you see in this, we will see that we will write the equations for all these marginals, and in the end what you just remember is just the equation for the first marginal. But of course, in this equation for the first marginal, somehow you have a lot of information about the other marginals. Okay? And maybe this will be my last comment for today. It's about this propagation of chaos. So I said that more or less this entropy tells you something about the correlation. In fact, that each time you have a collision, you have a little bit more of correlation and a little bit less, and you retain. As you just forget this correlation, you lose some information. Okay, but you see that there is something in this approach which is not really the original idea of Boltzmann. The original idea that you have for this system is that you should have some mixing property which comes from this collision. Okay? So the idea that you have is that chaos, the fact that you have kind of disorder, just comes from the fact that you have a lot of collisions. And actually collisions should be very good for chaos, while here in this proof, this is exactly the contrary. Okay? Each time you have a collision, this is very bad. Okay? You lose a little bit of information, and so you are not exactly counterized. You start from something which is exactly counterized, and each time you have a collision, Then you introduce a little bit of correlation, and then each time you are saying that the situation is worse and worse. Okay? And I think it's really important to see that it's probably not the original idea of Boltzmann and the original idea of thermodynamics, because probably why this description works well is not because at some point someone has decided that everything should be independent, but just because you have some mixing property, and that this is something. So, and for this mixing property, of course, collisions are very good. Okay, so maybe I can just give this one. So this is really important because it's related to these other comments that I have made about the proof and this short-time restriction. Of course, we will be interested in having a proof for very long times to see the relaxation but you see that there is a point which is really important. So we will see the proof that we will not use dissipation. Okay, dissipation is something which is really important to understand this propagation of chaos, this correlation, and you will see that the proof, Langford proof, doesn't use this dissipation at all, and actually the problem is just to identify what should be the dissipation. Because of course in the system, in the microscopic system, you will start from this microscopic system, and of course everything is reversible, nothing is dissipated, the energy is constant, everything is constant. Okay, so you really have to understand the relation, the connection between dissipation and correlation. And this is something which has still to be done. So if you have some ideas about this, of course, they are more than welcome. So I think I will stop here for the general presentation of this subject I found very interesting. We are really open to any question. And I will enter more, say, mathematical description of these results tomorrow. Thank you very much for your attention.